Hi, welcome. It's a quiet room. It settled down quickly, so people are excited about this. So I'm sorry to say that Ed Schlesinger wasn't able to make it this afternoon, although he's going to try to be here for some of the refreshments, so he knows where to be when. So I'm Lori Graham-Brady. I'm the Vice Dean for Faculty, and I'm thrilled to be here. So good afternoon, and welcome to the 2025 Don P. Giddens Inaugural Professorial Lecture Series. It's my pleasure to be here with you to honor Ishan Barman, a professor of mechanical engineering with joint appointments in the Johns Hopkins Sidney Kimmel Cancer Center and the Russell H. Morgan Department of Radiology and Radiological Science. Professor Ishan's research focuses on biomedical imaging and bioengineering using biophotonics, nanomaterials, and artificial intelligence to analyze complex biological systems and address questions relevant to both fundamental biology and applied clinical research. The Barman Lab, I think many members are here. The Barman Lab engineers nanostructured probes for ultrasensitive detection of specific molecular species through surface-enhanced Raman spectroscopy, capturing intricate tissue changes predicting disease progression. This work aims to identify different spectral markers for cell types, early cancer detection, and insights into disease progression and treatment monitoring. His talk tonight will showcase key innovations developed over the past decade, including virus sensing and surveillance platforms, DNA nanotechnology-based probes for single molecule detection, and AI-assisted quantitative phase imaging for tracking cellular dynamics. I'd like to take a brief moment to recognize Don Giddens, for whom this IPL lecture series is named. Don Giddens was the 5th Dean of Engineering at Johns Hopkins and a professor of mechanical engineering, appropriately enough. So now it's my pleasure to introduce Gretar Tryggvason, the Charles A. Miller Jr. Distinguished Professor and Head of the Department of Mechanical Engineering.
Okay, it is a real pleasure to introduce Professor Rohit Bhargava, who is the founder professor of engineering at the University of Illinois at Urbana-Champaign, where he is the director of the Cancer Center at Illinois. His primary appointment is in the Department of Bioengineering, joint appointments in several engineering departments and chemistry, as well as in the Carl Illinois College of Medicine. Professor Bhargava graduated with a dual degree from the Indian Institute of Technology, New Delhi, in 1996, and received a doctoral degree from Case Western Reserve University in 2000. After a stint at the National Institute of Health, he has been on the faculty at Illinois since 2005. Professor Bhargava is widely recognized for his research on chemical imaging and advances in theory, instrumentation, and application in cancer pathology. And with that.
Good evening. I want to start by congratulating Ishan on his stellar career thus far and today's milestone recognition. Indeed, professorship at a prestigious institution like Johns Hopkins for bioengineers is a career milestone. So Ishan, congratulations to your family, first of all. And on behalf of all of us, we want to thank them for the commitment and contributions they have made to your success. I also want to acknowledge your colleagues, fellow faculty members at Hopkins, collaborators across the world, staff, and students who have been part of your journey and undoubtedly are celebrating with you and you from near and far today. Thank you for allowing me personally to join in this joyful celebration. I'm, of course, deeply humbled and honored to be part of this occasion for you. And I'm sorry I couldn't be there in person, but I'm thinking of you and wishing you all the best from the West Coast of the United States. I first met Ishan nearly 15 years ago. As I recall, it was at a trip to MIT. And Ishan was one of my student hosts. Even before I met him, I had met his other colleagues who assured me that I was about to meet one of the smartest people in the spectroscopy lab at MIT. While I had been warned, the conversations with Ishan that afternoon went far beyond just smart talk. As all of you know, the ideas with Ishan come very fast, and every conversation is very stimulating, very deep, and certainly very exciting. Even from those very few hours of meeting with him, it was very clear that he was not just a scholar of the deepest caliber, but also one of the most innovative people that I was to meet during that visit and subsequently. I've been fortunate to have a ringside view of his work for the last 15 years or so, and we have all come to admire that his work is rooted in deep scholarship, broad understanding of the field, and motivated by truly important problems. He's not afraid to take on long-standing problems that have been difficult to solve, and then come up with solutions that perhaps are not common. When you read what he's actually done in every case, you have to admire the clever solution, the thoughtful treatment of the results, and the care with which the research is not only conducted, but how it is explained and its implications understood. I was familiar early in his career with his work on developing spectroscopic imaging tools for diagnosis, including Raman spectroscopy for monitoring conditions such as blood glucose and looking at glycated compounds within blood. And he has certainly continued on that path. One of his recent works was to use Raman spectroscopy to look at TSH from human patient samples using an immunoassay. In all these cases, he was able to use essentially a label-free technique, much like many of us in the spectroscopy world. But it's quite unique in the biomedical world. Even in our scientific circles, the researchers are usually divided between those who stick to label-free approaches or those who use labels. But Ishan is one of those people who crosses both domains quite easily. In addition to the label-free Raman spectroscopy that I talked about, he's also developed technology using laser-induced breakdown spectroscopy, light scattering, plasmon-enhanced spectroscopy, even fluorescence imaging. And not just satisfied with these technological modalities, his work has spanned silver nanoparticles, polymer particles, engineered nanoparticles of different shapes like stars, as well as machine learning and artificial intelligence, not just recently, but many, many years ago. I'm just sharing a snippet of the breadth of these applications, not only to remind you of the breadth of his contributions, but also the breadth of his intellect and his talent. It takes a truly special person to span so many fields, yet continue to have impact and have quality that is driven by applications, that is motivated by human health, and yet involves fundamental science and technology at an impressive level. Most of our clinical colleagues also will recognize these approaches as basic scientists like us do. Ishan's not just a fantastic scientist, but he's also a great mentor. His mentees have won many national awards. They're all successful in their careers. And there's a whole next generation of scientists from his lab that are amplifying his impact further. An impressive quality of all these trainees is how he emphasizes with them proficiency in basic science, as well as achievement in something that has truly mattered to society. I've also attended several of his lectures personally, and just every time I hear him speak, just come away with a feeling that I wish I could speak like that. Certainly learn something new every time he gives a talk, and I'm sure he's not just a great scientist in our scientific forums, but a great teacher in the classroom. It's always a real pleasure, and I'm going to miss it today. This makes me doubly regretful that I couldn't be there in person, not just to celebrate him, but to learn from him. So I hope you have a great event, and I'm sure it's going to be a wonderful lecture. I look forward to listening to this lecture online. So congratulations again, Ishan. While this is your first lecture as an appointment at the full professor level, this is by no means a culminating event. I hope you will mark today as just the beginning of many more exciting things to come from your lab. I wish you all the best in the coming years and for the rest of your career. I'm sure it's going to be stellar. All the best.
Okay. Thank you so much for the kind words, Rohit. And Laurie, no pressure now. Delivering this lecture is an immense honor and a deeply meaningful recognition. It's truly meaningful because it recognizes not just my work, but the incredible efforts of our team, of our brilliant team. Research, after all, is rarely a solo sport. It's a full contact team effort with plenty of experiments tackling us along the way. On this occasion, I'm delighted to share with you how we are leveraging some of the elegant properties of light to decode human pathophysiology. So sit back, relax, and enjoy it. In biology, imaging is a major driver of discovery. Many moons back, Richard Feynman had once famously said that it's very easy to answer many of the fundamental biological questions. You just have to look at the thing. 60 years later, dramatic improvements, particularly in fluorescence imaging, allow us to view increasingly smaller structures inside cells and tissues, visualize specific molecules, and study their dynamics. And yet, labeling may perturb the function of a molecule, and it limits the capacity of discovery as it is only applicable to known species. But you have to wonder, could we perform the same quantitative imaging without using any labels whatsoever? Mind liquidation time, we are already there. Raman microscopy offers multiplex molecular fingerprinting in live unstained biological samples. Quantitative phase imaging is rapidly emerging as a powerful approach as it offers nanoscale sensitivity to morphology and dynamics and 3D imaging of completely transparent structures. Allow me to share with you how we are leveraging these tools for diverse biomedical applications today. Our research interests reside in engineering innovation for analysis of complex biological systems, as is required to address questions important to both fundamental biology and applied clinical research. More specifically, our laboratory's research interests reside at this interface of optical spectroscopy, nanotechnology, and AI. Optical spectroscopy allows us to analyze single cells and develop wearable sensors, providing unprecedented sensitivity to detecting biological changes. Taking it a step further, spectroscopic imaging across various spatiotemporal scales provides a bridge between chemical and morphologic analysis. Artificial intelligence then allows us to dissect, slice, dice, analyze these increasingly complex data sets, improving techniques such as liquid biopsy. And finally, nanotechnology bridges these efforts by engineering smart materials for tumor imaging and for studying cellular biophysics. Beyond these areas, we're also really excited about our nascent forays into emerging fields such as quantum sensing, soft robots, customizable UAV swarms, and bioprocess monitoring that continue to broaden the scope and impact of our research. From this broader research program, I'd like to share today 3 vignettes with all of you. Briefly, we'll start out by discussing how DNA nanotechnology is making a substantial difference to creating a new generation of highly sensitive and reproducible imaging probes with applications ranging from single molecule sensing to quantum biology investigations. Second, I want to discuss our many years long foray into the world of single cell analysis and how that initiated the development of cell wraps and cell traps. It allows us to isolate and study these cells with unprecedented control, critical for understanding disease progression and therapeutic responses. Finally, I'll share our work on in vivo tumor detection. Here we are engineering smart probes that don't just wander aimlessly in the body, but assemble inside targeted cancer cells, emitting distinct optical signatures, almost like a molecular GPS saying, hey, the tumor is right here. So, one of our main tools in the explorations, in all of these explorations really, is optical spectroscopy. Now, optical spectroscopy is unique amongst experimental techniques in that it can be performed in physiological conditions, achieve high molecular specificity, and explore dynamics on timescales ranging from attoseconds to days. Of these, Raman spectroscopy stands out owing to its sheer information content. Raman spectroscopy, as many of you know, is a fundamental form of molecular spectroscopy that is widely used to investigate the structures and properties of molecules from their vibrational transitions. Here is a photograph showing the Raman spectroscopic effect. Now, a 488 nanometer laser beam here is going through a vial of liquid cyclohexane, and what you see on the right over here, is the Raman scattered light, since the elastically scattered photons have been rejected by that bandpass filter. Now, here, for no good reason, I show you the Raman spectrum of glucose. Well, there is a good reason. There is, you can see all these sharp peaks, right, belonging to the skeletal modes, the stretching modes, and the bending modes, and that kind of reinforces the sheer information content that you can get from just one single spectrum. Now, Raman spectroscopy has been around for a long time. I can see a lot of you saying that in your heads. Yet, what's so new today? Well, numerous biomedical applications of Raman spectroscopy have been reported. For instance, there's that speaks of a Raman probe that can provide live local detection of cancer cells in the human brain. That's very impressive, and that's a decade back, right? So we can do so much with Raman spectroscopy and innovations there. While we love the molecular specificity of Raman spectroscopy, the problem with Raman is you often just get a handful of photons to work with. Surface-enhanced Raman spectroscopy, or SERS, is a surface-sensitive technique that enhances Raman scattering of molecules adsorbed on rough metal surfaces or on nanostructures, as you see right over here. The quantum of enhancement, often 8 to 10 orders of magnitude, repeating for emphasis, 8 to 10 orders of magnitude, primarily depends on the presence of these localized surface plasmons on the noble metal nanoparticles. Now, SERS, as I'll call it from now, can be performed using two types of substrates. You can have colloidal substrates and solid substrates. Colloidal SERS utilizes these nanoparticles, such as gold nanostars and bimetallic particles, which provide considerable enhancement but require careful preparation and control. Solid substrates, such as these periodic nanostructure arrays, offer more reproducible and scalable platforms for measurement. There is a catch, though. The overall intractability in controlling enhancement has led to the theorization of the so-called SERS uncertainty principle. So highly enhancing substrates often suffer from poor reproducibility, while more uniform and reproducible substrates, well, they may not achieve the same degree of signal amplification that I just spoke of. And that is precisely what we are looking to solve in our first piece today. Welcome to this beautiful world of plasmonic nanocavities, and specifically how we are harnessing DNA nanotechnology to improve surface-enhanced spectroscopy. To address these, or overcome, perhaps a better word, the SERS uncertainty principle, we turn to optical metamaterials. Now, these engineered nanostructures that you can see over here, these engineered nanostructures exhibit extraordinary optical properties by precisely manipulating electromagnetic fields at the nanoscale. But the question is, how do we achieve this in reality? Because aggregation in colloids, and I'm sure all of you will agree, is notoriously irreproducible. One powerful approach to designing these materials is by using DNA-directed self-assembly. DNA offers a programmable way to organize nanoparticles with high precision, ensuring both tunability and reproducibility. By leveraging the sequence-specific hybridization, we can precisely control nanoparticle spacing and spatial arrangement, dynamically tuning the optical properties of these assembled nanostructures. And that is incredibly powerful. Drawing on these emerging concepts, then, we've engineered highly precise and robust nanocavities that we call DNA strobe by using these silicified DNA scaffolds for spatial organization of these discrete gold nanoparticles, as you see right over here and here. Now, DNA silica hybrid structures possess excellent chemical resilience, chemical inertness, and mechanical resilience that are not achievable on bare DNA origami. Yet, these concepts have not been used to generate well-defined plasmonic nanocavities. Our structure is very simple, or at least initially it's very simple. It's assembled through DNA hybridization of two complementary DNA strands, one of which is associated with the satellite nanoparticle and the other with the core nanoparticle. Now, despite the apparent conceptual simplicity of DNA silicification, it's a hard strategy to implement in practice because of the electrostatic repulsion between the anionic DNA phosphate backbone and the silanol precursors. Here we use the positively charged Tmaps molecule that you see right over here, which serves as a co-structure directing agent. The siloxane functional groups in particular provides direct co-condensation sites for the silica shell to grow. All in all, what I'm trying to say is that DNA is frozen inside this ultra-thin silica shell, thereby retaining all the initial structural integrity. We fabricated various hierarchical nanoassemblies using that concept with increasing complexity and different sizes of gold nanoparticles, as you can see over here, from gold nanodimers to core satellite constructs to core satellite constructs, as you can see from these different ACM images. Now, these DNA strobe nanoassemblies displayed excellent chemical inertness under both neutral and acidic conditions. In contrast, the core satellite nanoassemblies without DNA silicification become aggregated. They become aggregated under acidic conditions, making it much less suitable for use in biological measurements. Crucially, the DNA strobe arrangement affords much better control of the nanogap. And by nanogap, I mean the gap between these two particles. And that is important because that is exactly what leads to controlled yet very large plasmonic enhancement, negating the previously stated Sear's uncertainty principle. One of the real questions that we came up with, or we wanted to solve, is whether we can see molecular events at these plasmonic hotspots. And we believe the answer is yes, with evidence to back it up. Now, in panel A over here is an illustration of a stochastic single molecule event at a specific time point. Here you can see one Raman active molecule just moseying along inside the hotspot and then wandering off in its own merry way. This switches the Search signal on and off. Now, by repurposing a turf microscope for wide field excitation, we acquired Raman images around these plasmonic nanocavities. Here in panel B, I show you the time trace of the Search intensity fluctuation at one such hotspot. Now, standard Search images were acquired with an acquisition time of 10 seconds, and the DNA strobe constructs were presented as blurred spots, expectedly so. Yet, by fitting the point spread function to a model function, the emitting center, i.e. these plasmonic hotspots, could be uniquely determined at the centroid, just like super-resolution fluorescence imaging techniques such as STORM. The fitting process was repeated for hundreds of temporal Search image frames till all the plasmonic hotspots were accounted for. The final spatial profile that you see over here is constructed or reconstructed by superimposing all of these determined centroids. What we see, though, is quite remarkable. The centroids are visible as discrete, bright spots around an annular ring, which bears a striking resemblance to the original core satellite architecture with all of these hotspots. What's more important, and what I want to direct your attention to, is the length scale there. This is 200 nanometers. These ones are 20 to 30 nanometers. That is a single molecule event. A particularly interesting application of such a synthetic approach is in the creation of plasmonic nanodiamonds. As it turns out, diamonds, they're not only good for jewelry, but also for unlocking the secrets of biology at the quantum scale. While nitrogen vacancy centers and diamonds have emerged as these promising quantum emitters, the tantalizing possibility of coupling those with, for example, these kinds of broadband plasmonic structures has not been realized. And that's a shame because it would lead to ultra-sensitive biolabels. The reason it has not been combined is because it's technologically challenging to create these freestanding structures that are diamond-based imaging probes with enhanced resolution and enhanced brightness. Well, here we leverage DNA self-assembly approach to develop the first of its kind freestanding plasmonic nanodiamonds, which feature a completely closed plasmonic nanocavity that encapsulates a single nanodiamond, as you can see right over there. We call these structures rings, resonance indicator of nanodiamond and gold. We believe that has a nice ring to it. Oops, sorry. This design facilitates a more homogeneous electromagnetic environment and a much larger photonic density of states for accelerating the emission dynamics of the enclosed NV centers. Here I show you correlative characterizations using SEM, dark field, and film microscopy. But what I want to direct your attention to is the right panel. What you see over here is that the mean lifetime of the NV centers on bare ITO glass is 7.94 nanoseconds, while when they're enclosed inside this plasmonic nanocavity, i.e. the ring structures, that is 0.45 nanoseconds. That's an 18x enhancement in the emission rate. Moreover, the same NV centers, as you can see right over here, were found to exhibit a 50-fold enhancement in the fluorescence intensity, which is a combined effect of the excitation and radiative decay rate enhancement. Together, these two results underscore the exciting perspective of using these ring nanoprobes as ultra-sensitive biolabels in imaging experiments. One particular application I want to direct your attention to is their use as ultrasensitive magnetometers to investigate non-trivial effects or non-trivial quantum effects in biology. Imagine being able to detect the minute or minutest of minute magnetic fields that arise because a single ion crosses an ion channel. Could we detect that? We believe we can with these ring structures. If we can, that would lead to serious breakthroughs in mapping neuronal activity and picking up early signs of diseases such as cancers. So stay tuned for more on this in the days to come. Let me with that now pivot to the second piece and move up a few length scales. While doing so, we're going to talk about single cell analysis. Single cell analysis has become particularly important in the mechanistic elucidation of biological functions in light of the emerging consensus that cellular heterogeneity exists even within an isogenic cell population. Now, cellular heterogeneity is missed, sadly, by population analysis, as most classical methods report on the mean expression level of a bulk cell population. Furthermore, snapshot analysis can confound different dynamic behaviors. Flow cytometry, for instance, can reveal cellular heterogeneities but cannot detect the underlying dynamics. To address this, we wanted to generate a 3D self-assembling platform that can follow and predict a cell's behavior and function over a period of time. In order to do so, partnering with Dr. David Gracias' lab in the Chemical and Biomolecular Engineering department, we worked on and reported a molecular mirror. Well, almost. This is a new shell-based spectroscopic platform that we call Mechanical Trap Surface Enhanced Raman Spectroscopy. That's a mouthful, so we call it MT-SIRS for short. MT-SIRS allows capture and 3D molecular profiling of the cell membrane of single live cells. Here, we first fabricate arrayed single-cell grippers composed of biocompatible silicon monoxide and silicon dioxide. The energy required to actuate these grippers, so they obviously have to go from whoop to whoop. The energy required to actuate these grippers is derived from release of residual stress in these films. So there is no batteries, no active components, no wires. Next, by leveraging the functionalization of the inner surface of the traps with these plasmonic gold nanostars, and by exploiting the conformal contact, our platform enables non-perturbative acquisition of SIR spectra of the cell membrane constituents, and that's how we get the molecular mirror. Here we selected these two silicon-based oxides for our single-cell grippers based on their biocompatibility, but also because of the self-curling properties. As you can see right over here, these grippers are fabricated with flexible pre-stressed bilayer hinges connected to these rigid segments. The pre-stressed bilayer were constructed from E-beam evaporated thin films of silicon monoxide and silicon dioxide. This particular combination provides a sufficiently small radius of curvature for single-cell gripping, with radii as small as 750 nanometers. The rigid segments, on the other hand, were formed from thicker films of E-beam evaporated silicon monoxide. Now, the grippers can be fabricated in a wide range of sizes and shapes for capturing different objects of interest with a high degree of tunability. We were able to fabricate grippers as small as 10 micron to as large as 70 micron. Well, we can easily do it even larger, tip-to-tip size. Now, since the films are also optically transparent, the cells captured by the grippers can be readily observed using optical microscopy. So here you can see 3 of these fluorescent expressing cells that have been captured by the grippers, and you can actually see that using optical microscopy. We then set out to validate 2 important capabilities of the MT-SIRS platform, namely the ability to measure molecular signatures of an entrapped object and the capability for dynamic in situ measurements. For these experiments, we used Janus-like microbeads with spatially distinct molecular surfaces. One hemisphere of the microbead, which hopefully you can see in panel A, was coated with a thin gold layer and then functionalized with nitrothiophene, which is a Raman reporter. The resultant spatial map clearly shows you that the SIR signal of NTP is much stronger in the selectively functionalized hemisphere than in the other hemisphere. Well, that's along the line, so nothing great there. But what we do based on that is impressive, because based on the stack of 2D spectroscopic images, we generated a 3D map of the distribution of NTP on the microbead, which you can see in panel C over here. And this closely resembles the gold pattern observed in the corresponding S. In a separate set of measurements, we also observed the temporal decay of the surge intensities recorded from the entrapped Janus microbeads in the presence of oxidants. Now, what does the oxidant do? Oxidant essentially just cleaves the nitrothionol. So over a period of time, you can see this particular peak reduce in intensity. The ability to differentiate between the decay profiles corresponding to the two oxidants reflects the quality of in situ dynamic measurements. There's many other interesting measurements that I have to skip in the interest of time today, but suffice to say that the MT-SURS platform presents some very unique opportunities. Yet one of the limitations of biosensors that are based on 2D rigid substrates is that they are definitionally incapable of conformally wrapping a soft cancer cell or an irregularly shaped object. To address this unmet need, we have engineered an ultra-thin graphene nanoparticle hybrid skin that is thermally responsive and can be triggered to self-fold and wrap around any 3D object in a highly conformal manner, simply because it has superior flexibility. Now, graphene, as you all know, provides an atomically thin monolayer structure with good chemical inertness, biocompatibility, and crucially, low bending rigidity. Here, graphene is combined with silver nanocubes to permit strong plasmonic enhancement. The other critical piece, which you see right over here, is the grafting of the polyanisobutylpropyl acrylamide or PNI/PM brushes on the graphene that endows it with a unique temperature responsive folding capability. What I show you here is the mechanics of the operation using a representative dumbbell-shaped skin. The self-folding process, as you see in panel A, is essentially that the two petals of this dumbbell-shaped skin fold towards the center when heated in water to 37 degrees centigrade. Why does that happen? Well, upon increasing the temperature above the lower critical solution temperature of PNI/PM, roughly 33 degrees centigrade, the densely grafted brush layer undergoes a significant shrinkage in volume, approximately 50%, while of course graphene does not shrink any. The internal strain mismatch induces folding of the overall structure, as you can see on this slide. An attractive feature here is that we can tune both the density and the arrangement and the spatial distribution of the plasmonic nanoparticles on the skin using photolithographic patterning. Of course, a higher density of silver nanocubes means stronger plasmonic enhancement, but it also leads to higher bending rigidity, and that is not so desirable beyond a certain critical point. So there's a little bit of a trade-off there. Now, the low bending rigidity of the skin means we can not only wrap cells, but also wrap 3D objects with a highly irregular geometry. I want to show you something crazy that we did here. What you see here is an oxide daisy pollen. Not that I know much about daisy pollens, but nonetheless, this has an average size of 35 microns, and it has, of course, an irregular and spiky geometry. Now, it's very challenging for conventional rigid biosensing substrates and devices to form conformal contact, to form intimate contact with such spiky microparticles. Here, on the other hand, we observe that our ultra-thin graphene nanoparticle hybrid skin conformally wraps the surface of the pollen, including its spikes. And if you see it closely, you can actually see the formation of characteristic wrinkles of skin-like materials along the edge and the bottom of these spikes. This intimate contact then allows high-resolution 3D surface chemical mapping. To demonstrate this feature, the surface of the pollen was adsorbed with rhodamin 6G molecules prior to its encapsulation with the skin. The right panel over there shows you the Raman spatial mapping using the rhodamin 6G peak at different Z planes. What you see is that the spiky feature of the pollen particle show significantly stronger intensity along the peripheral region compared to its internal area. Now that we have combined optical spectroscopy and nanotechnology, I want to shift gears once more and bring AI into the mix. The effort I'm going to describe briefly started during the COVID-19 pandemic. As we all learned all too well, viruses evolve rapidly and unpredictably, challenging the effectiveness of disease diagnostics. A crucial step in controlling such outbreaks is the timely and accurate detection of the viruses. Our method is really simple, almost too simple. You place a drop of saliva on a substrate and shine light on it. The interaction of light with the saliva sample in the presence of a substrate gives rise to a molecular fingerprint, almost like a barcode that we can decode using AI in order to pinpoint the presence and the concentration of a virus. To boost the signal significantly, we fabricate large area nanostructured substrates. These are, for instance, on the top left, called field enhancing metal insulated antenna arrays, or simply metal insulated metal, with multiple alternate stacks of silver and silica. Using state-of-the-art nanoimprint fabrication and transfer printing, we've been able to realize not only rigid but flexible sensor surfaces, which is critical for future implementation in wearables. The final piece is the uncovering of and differentiating the virus signature from that of the myriad other constituents in complex biological media, such as saliva, and this we get AI to do for us. Crucially, the detection methodology eliminates the need for any virus-specific recognition elements, so no antibodies, no aptamers, no other reagents, and therefore holds promise for detection of mutated viruses without substantial alteration to the platform. Now, the good part of that is it allows us to think of broader virus surveillance and monitoring and be better prepared for the management of future outbreaks. Not that I want any, but well, if there is one, we are better prepared for it. So how does it stand up? How does it look? Let's take a look at our very first iteration. Here we use random forests, an ensemble learning method for classification. And as you can see from panel B and panel C, which represent the class estimation, performance, and the confusion matrix respectively, the degree of classification accuracy for SARS-CoV-2 and H1N1, both being respiratory viruses, is roughly 85%. And for Marburg and Zika, two other important viruses, it's slightly north of 95%. Now, these results were returned in less than 20 minutes from when the samples were dropcasted onto the substrate. We also generated binary classifiers, as you can see in panel E, right over here. For comparison, where we lumped everything but SARS-CoV-2 into the so-called others category, and here we observed about 93% accuracy. You can see the same in the ROC curve, the receiver operating characteristic curve, where the area under this green curve is 0.98, with 1 being perfect classification. Indeed, we even reached that if we compare the respiratory infections, that is to say SARS-CoV-2 and H1N1, versus non-respiratory Marburg and Zika. Well, this work led to the filing of a couple of patents through JHTV, which was licensed to and became the core technology of our startup company called Raman ID that we founded in spring 2022. Following 2 years of solid technical and business development and a lot of sweat and work, Raman ID was acquired by NomadX in April 2024, a very exciting journey with lots of learning sprinkled in. Following this acquisition, NomadX's sensing unit has grown into a dynamic 25% entity right now, and NomadX leverages our SIRS technology to develop solutions for in food safety, in water quality, with future plans of expanding into rare disease diagnostics. Okay, pivoting to the third and final vignette that I want to discuss today, let's move up another few length scales in an effort to enable smarter tissue visualization. Our efforts here are driven by a simple but critical need. Doctors must be able to see cancer clearly where they need it the most, when it matters most, and that is in the operating room. The human eye, as we all know, can only see so much. And even with advanced imaging techniques, you name them, MRI, CAT scans, a surgeon's ability to precisely differentiate tumor tissue from healthy tissue is still a major challenge. This means that in many cases, determining the exact tumor boundaries still relies on a combination of experience, guesswork, and post-operative pathology. No, I'm serious, right? And here's the problem. If you remove too little, you run the risk of leaving behind residual cancer cells that could lead to recurrence. If you remove too much, you risk damaging healthy tissue that's critical for function. And as you can see, these numbers are staggering across the board. And I've just taken 2 examples over there. But for all kinds of tumor types, the numbers are staggering. So how do we fix this? We need better real-time imaging tools that can provide sharp, molecularly specific contrast without having to wait for hours or days. technologies that don't just highlight suspicious areas, but actively guide the surgeon with incredible precision. And that's what we are hoping to do. Some of this work started a long time back, and with simple, spontaneous Raman spectroscopy, no dyes, no labels involved here. So we devised a minimally invasive Raman spectroscopy-based fiber optic probe, which you can see in the top left panel, that allowed real-time identification of microcalcification status and breast lesion type. Based on data that we collected from 40 patients undergoing stereotactic core needle biopsies, our machine learning algorithm was able to accurately detect more than 85% of the breast lesions. That's impressive. But what is important is to be able to translate this from the bench to the bedside. So our next goal was to be able to do that. And the system at that point of time was literally sitting on a bench, on an optical table, and we needed to translate that. So in an effort to do so, we had to constrain the outer diameter of this probe to 2 millimeters, which it was a significant technological challenge, so that it could fit with existing core needles that are used for biopsy. So you want to have seamless integration into the existing workflow. Furthermore, our spectrometer unit here needed to be fundamentally redesigned and assembled so that it could squeeze within the narrow confines of a radiology suite and be placed underneath the bed where the patient was laid face down for the procedure. Here I show you a vacuum-assisted stereotactic breast biopsy underway, and here's a system positioned for action. More recently though, partnering with Professor Jeff Bulte in the School of Medicine here, we've opened a new avenue for targeted tumor imaging using molecularly programmed probes. Specifically, we have designed a new class of nanoprobes that we call NanoSaber, tailored to exploit the biochemical environment of tumor cells. These probes are designed to transform into supramolecular structures exhibiting distinct signatures in the presence of a target enzyme that is specifically overexpressed by only one particular kind of tumor cell. This creates a direct link, a causal link between enzyme activity and the Raman signal. These probes these NanoSaber probes possess a cell-penetrating peptide which helps them enter tumor cells. Now, once inside these tumor cells that overexpress legumin right over here, such as highly metastatic prostate cancer cells, nanosabers undergo a two-step transformation. First, it gets reduced through intracellular glutathione, and then it gets cleaved by the legumin. This triggers the formation of alkyne dimers, which then self-assemble into much larger nanoparticles via pi-pi stacking interactions. Crucially, the formation of these larger assemblies, what does that do? It prevents them from being pumped out of the cell, increasing local concentration and therefore sensitivity in imaging the tumor and the tumor aggressiveness. The enzyme-triggered self-assembly inside these legumin-rich metastatic cancer cells also create very distinct Raman signatures, as you can see right over here. So the nitrile signal, for example, goes down inside these DU145 cells, which have high legumin expression, but not inside these low legumin expressing LNCAP cells. To test this, or test this theory, we incubated two prostate cancer cell lines, again the DU145 and LNCAP, with Alexa labeled NanoSaber. Now the green fluorescence over here represents self-assembled alkyne dimer nanoparticles that are activated by legumin. What you can see here is that the DU145 cells, which express high levels of legumin, show a strong intracellular aggregation of these nanoparticles, while the LNCAP cells, which have low metastatic potential and low legumin expression, well, not so much, right? This confirms that NanoSaber's activation is highly enzyme-specific, a key requirement for precision imaging. Finally, we take this to the next level, in vivo tumor imaging. After IV injection of NanoSaber in mice bearing both DU145 tumor and LNCAP tumors, we use Raman imaging to detect this signal. Now, the green regions here correspond to the alkyne peak at 2120 wave numbers, which essentially tells you how much of the nanosabers are assembled in the tumor over there. And as expected, you can see the DU145 tumors have a much stronger signal compared to LNCAP, where at least I can't see any. So the lower panel here confirms, the lower panel is fluorescence imaging, it confirms exactly what we saw over there, because the legumin expression aligns quantitatively well with the Raman signals in the upper panel over there. In a separate set of studies, we also tried a variant of these molecularly programmed probes to detect other enzymes, such as furin, that are overexpressed by colorectal cancer cells with similar levels of success. Together, these studies underscore the broad potential of these probes, these molecularly programmed probes, to detect enzyme overexpressing tumors, paving the way for a real-time molecular roadmap that can assist surgeons through these complex procedures. With that, let me turn to the future for a moment. I want to give you a glimpse into some of the innovations we have in the pipeline, ideas that are pushing the boundaries of imaging, autonomy, and exploration. First, let's take a look. Decoding neuron-astrocyte interactions with label-free quantitative phase imaging. Imagine being able to watch the neurons dance, as you see right now, connect, disconnect, socialize, and interact with the local environment in real time. And it's interesting, it almost behaves as we do, connecting, disconnecting, socializing, and so on. This effort gives us fresh insights into brain activity, and we are seeing and reporting some fascinating results already. Next, the XR301 drone ecosystem. This is a squad of custom-designed drones working together on demand with an autonomous launch, recovery, and recharge system. This self-sufficient swarm can be deployed for first response, disaster relief, and so much more. And finally, our bio-inspired soft robotic explorers, which we have started building. Inspired by worms, these low-power, essentially self-charging robots are designed to crawl across diverse terrain, recording local environmental data. So lots of exciting stuff on the horizon here, and hopefully much more to talk about in the coming days. Let me now acknowledge those who have made this work possible. I've been incredibly fortunate to work with a very special set of individuals, a team of graduate students and postdocs, many of whom have gone on to establish their own research groups across the globe or take on impactful roles in the industry. Beyond that, we've had a number of exceptional undergraduate students, some of whom have led studies, earning first author publications. Together, their creativity, their dedication, their drive have been instrumental in pushing our research forward, and I could not be prouder of what they have accomplished. I want to next thank the Department of Mechanical Engineering, which has provided this very secure and fertile environment for our research program to thrive in. Its leadership, the faculty, our collaborators in the department, our mentors in the department, you know who you are, and to the staff, because let's be honest, without them, everything would come to a grinding halt. To my collaborators across the US and around the globe, many of whom are mentioned here and many of whom are also not mentioned here, I'm incredibly grateful for the collaboration, for the discussions, for the ideas and insights that they have shared over the years. It's a very incomplete list, but hopefully the message of gratitude is communicated. I wanted to thank also some of my mentors who have had a profound influence in my life. My PhD advisors, Michael Feld and Ramachandra Dasari. Michael, arguably the pioneer of biomedical optics, was a visionary, a giant of a man way ahead of his times. His passion for science has shaped and continues to shape much of my thinking. Ramachandra for his mentorship, unwavering support, and so much more, both personally and professionally. Quite simply, I wouldn't be standing here without him. I miss them both deeply today, more than I thought I would. I also want to acknowledge Yuki Ozaki. Yuki was the first person who prodded me, coaxed and cajoled me to work on CERS. So certainly that was a beneficial interaction or series of interactions. And Rohit Bhargav, who has this knack of asking really deep questions, and I've tried to emulate him a little bit in that regard. I want to take a moment to thank the two people who have shaped my life from the very beginning, my parents, Osim and Meeta Barman. Ma is a retired professor, and she instilled in me a deep appreciation for learning and intellectual pursuits. Her belief in me has always exceeded my own belief in myself. She's been my fiercest advocate and my most patient teacher. My father, his journey is one that deserves a lecture all its own. From a humble beginning to a career where he truly transformed the lives of countless people. If I can have a tenth of the impact that he's had, I'd have led a very worthy life. Whenever they visit Baltimore, I take them to my labs. Last summer when they were here, I was showing them around. And we passed a piece of equipment that we had just recently purchased, okay? And truth be told, I didn't have much of an idea of how that worked. So my parents looked at me, smiled, and said, okay, now you seem to be established. So to my parents, thank you for the sacrifices, their wisdom, and their belief in me. Which brings me to my wife, Maya. I was originally planning to sing a song at this point, but I don't have a great singing voice, and I fear I'd traumatize her forever. So let me stay with an anecdote then. The last time she heard me deliver a lecture, this is well before I was a faculty member, I was describing a silver gold sandwich substrate. I don't recall much else about the lecture, but at the end of the lecture, she came up to me and said, I'm not sure what you're speaking about, but it did not seem very appetizing. Maybe we should get a real sandwich now. So hopefully some of this work that I described today is a little bit more appealing. She's been my anchor through all the highs and lows, through all the late nights, through all the grand deadlines, the moments of excitement and the moments of doubt. I should also say I could not be prouder of her journey, of what she's achieved and the work she does. So thank you for being there always. And last but not the least, a shout out to our mini golden doodle Coco, who just turned 1 year old, as you can see in the bottom right picture. He's been a constant source of support, inspiration, and occasional chaos, mostly by making sure no Zoom meeting goes uninterrupted. He's probably saying at this point of time, I've been speaking for too long, and I probably need to wrap it up, which I will now. And thank you all for your attention and patience. Thank you.
Thank you, Ishan, for a wonderful lecture. Thank you, everybody, for being here and for all the people who contributed to this fascinating work. And I have a small gift of appreciation I hope you'll accept.
Yeah.
And congratulations again.
Thank you.
So everybody enjoy refreshments, and we'll fire questions your way.
Sure. Thank you.